So welcome to my talk about my book, Nano Comes to Life. The previous talk by Professor Raza was a perfect preliminary talk for the content of my book. She spent her time talking about her book and the failures of reductionism to actually treat cancer and how current medical paradigms are not good enough to treat the most deadly of diseases. She explained very well how our obsession with DNA and proteins and drugs that simply target molecules have failed to improve the treatment of cancer. The reason for this, as she just explained, is that for the last 20, 30 years, since the discovery of DNA, we've been trying to overcome biological complexity by just the study of DNA. In that sense, nanotechnology for many people, and especially for many biologists and biochemists working in pharmacology, was going to be just that. We would have nanobots that will fix our broken DNA. But the story I tell about nanotechnology is very different. And I would tell you how nanotechnology actually is key to embrace biological complexity and to make real breakthroughs in our understanding of biology and the improvement of medicine. The reason why we have become so reductionist in biology has mainly been for the history and the social context in which we do biology. So physicists started early on in biology, looking and fabricating microscopes. The microscopes gave us the first images of how biology is made. It's made of little bits. But the next level of complexity was very difficult to reach, because biology is made of molecules, and molecules are very small. They're at the nanoscale, so it could not be seen by microscopes. That meant that molecules were studied in crystals that they were used by X-ray diffraction in very unnatural ways. Out of this came, of course, the famous structure of DNA, for which Watson and Crick got the Nobel Prize, and for which the work was mainly done by Rosalind Franklin, and produced a picture of biology that was oversimplifying. We would just look at the genes, and the genes will tell us everything, and we will forget how the genes interact with the environment. But as we saw in the previous talk, this has not brought at all the results we expected. It was not only DNA. A lot of people, actually, he was working at the Royal Institution, like the previous talk was talking about, spent a lot of effort in trying to understand the structures of biology at the nanoscale, but always far from life, in crystals, in a very reductionist way. This led to a picture of biology sort of like this, from a biology look. A lot of building blocks that barely have a way of interacting with each other with science. There's no equations, there's no models, there's words between them. Science became a kind of theater between molecules. So as the previous talk was saying, the reason why we did reductionism for so long was because it was easy, and also because of many political agendas, such as colonialism and patriarchy. And of course, it was useful to create a vision of technology that would you have building blocks, and you will just be the structures out of them. But in parallel to the story of the development of molecular biology, nanotechnology happened in the 1980s. And what is nanotechnology? Nanotechnology is the capacity to interact and create matter at the nanometer scale. So that's the scales of hundreds or thousands of atoms, like 1,000 times smaller than the diameter of your hair. Very small indeed. So the tools of nanotechnology allowed for the first time to interact with matter at the nanometer scale. But this doesn't happen in biology departments, it happens mainly in physics departments. And the first microscopes, like this example I always show, allow us to not only see matter at the nanometer scale, but to manipulate it. So what you can see in this picture are a background. It's a scanning tunneling microscope image of a surface of copper, and the little atoms are the little balls at the back. And on top, there are little iron atoms. So these guys, Don Eigler in IBM in the 1990s, managed a way to pick up individual atoms and to arrange them in a circle. What you see here was the first realization of something amazing, which is that humans have the capacity to build matter and to interact with matter and to build things using atoms one by one. But what you can see in the middle is a ripple. Science, as nature is always playing a trick. The ripple are made of electrons. The electrons in the metal are trapped within the atom's quantum corral and present a ripple, like because they behave like particles as well as waves. But what it's telling you here is that even when you try in very simple systems like this one to just arrange atoms and build very simple structure, nature is never simple. It responds with very complex behavior. This is what condensed matter physics had done actually in most of the 20th century. It started to tackle with emergent phenomena. So this meant that physicists, even though they were creating tools for moving individual blocks, they also had the intellectual tools to start thinking about complexity, which is what was missing in most of biological research and still is missing now. So many people like us, when we started looking at matter at the nanometer scale, immediately we got interested in biology. Why? Because biology is made of nanomachines. The proteins, the DNA, they all have nano size. And why do they have nano size? That's what we were interested in. Why evolution created life out of matter at the nanometer scale? And life created amazing structures. One of the most beautiful is here, the ATP synthase, which you have in kilograms in your body. It's a little nanomachine that functions as a rotationary motor to catalyze chemical reactions. And that's already telling you, and the reaction was discovered by Hiroyuki Noji, that is already telling you why biology happens at the nanometer scale. At the nanometer scale, you're so small that you can get the energy of the environment to create movement. And that movement can be used to, for example, catalyze chemical reactions. And that's one of the things we wanted to understand when we started to move into biology. So I was one of the people that moved to use the new microscopes, the new tools of nanotechnology to look at life as it really is at the nanoscale, not in crystals, not in cartoons, but actually start seeing life as it happens in real time, moving, how it uses the temperature to move, to create their shapes. Biology is movement, and our new techniques will allow us to study that from the point of view of physics. There's no more words. We can actually start to do mathematical models of what we see. So, using these techniques, people started to look at the proteins that we knew they were just cartoons before that. So let me show you this beautiful example from Noriyuki Kodera from Kanazawa University. What you see here is a track of actin. You have actin inside all your cells. And on top of it is a myosin molecule. It's a protein. And if you see, it's making a movement on top of the track. This is how real proteins work. How does it do that? So evolution has created this protein, so it sits on the track with electrostatics and uses the water movement around it to create a movement forward. This movement forward is used in your cell for carrying cargoes, for producing tension. Every single movement in your body is actually mediated by the stepping movement of this molecule. And this is biology happens at the nanometer scale, because when you're so small, you can just use the movement on water around you, and your mechanical design will allow you to produce movement, pretty much like a windmill is able to rotate when the wind comes. At the same time, nanotechnology, that these things were happening, it started to come to the popular culture. The most famous book was Engines of Creation, that was starting to predict the future that we will have if we were able to harness the nature at the nanometer scale. In the meantime, in chemistry departments, people were starting to be able to fabricate the first nanoparticles. So in the 1990s, all the sciences were converging in the nanoscale. So the first attempts to use nanotechnology in medicine were at the same time, and they were done in a very reductionist approach again. It was basically loading drugs that they were used in normal chemotherapy treatments into nanoparticles. The idea is that because you load them in nanoparticles, they're able to navigate better and find the tumors. However, this didn't translate in better cancer treatments, as we saw in the previous talk, because basically they reproduce the same way of thinking as normal pharmacology. And moreover, the body is also able to clear nanoparticles. Biosensing was another area that was creating a lot of promise of nanotechnology. And like cancer, it also failed. As you know, for example, with the stories of Theranos, it was a huge company that was created and it was going to create very cheap diagnostics. Again, it was overlooking the complexity of biology and failed. Every time we try to create either a treatment or a new technology that doesn't take into account the reality of biology, it fails. So, at the same time, other people were using nanotechnology to start a very different approach. Was using the molecules of life, DNA or proteins, to create materials that could not be created using normal top-down approaches in material science. Perhaps the most successful of these technologies has been DNA nanotechnology. So the idea was from Adrian Simon, who decided to use DNA as building blocks of any shape, just using the DNA as little Lego blocks and use their interconnectivity to be able to create the shapes he wanted. Actually, he got inspiration from Escher in a story I don't have now time to tell. And the breakthrough came perhaps here with the creation of DNA origami, where it was shown for the first time that you can design any shape of DNA in the computer and then get a long DNA, usually a viral DNA, and some staples that you would program in the computer to create literally any shape at the nanoscale with DNA. This was followed by people that managed to do the same in 3 dimensions. And these days, you can also build absolutely any shape, even 3D, with DNA. Teddy bears and all sorts of things have been constructed out of different strategies to create DNA. But perhaps the most interesting things are starting to happen now. So DNA, you can basically build shapes, but it's difficult to give it real uses in real life, although people are trying very hard. And also, it's just reproducing a kind of top-down approach to technology in which you just build building blocks to build something different. But I think the real breakthrough came actually from Seattle and many other people working in protein structure, who for the first time, not long time ago, started to be able to create to predict the protein structures in the computer. The protein structures that I showed you at the beginning, the rotations, the movement, are very difficult to predict. That's why we have X-ray diffraction. But using a very interesting combination of computer power, physics, and protein structure, and crucially, evolution into the calculation. These guys managed to break one of the biggest scientific problems of the 20th century, which was to predict protein structures. And as soon as they did that, they started to design in the computer proteins that don't exist in nature, but they use the building strategies of nature in the computer. And then they went back to the cell, and then were able to put pieces of DNA inside cells so the cells could produce these structures for them. This is the first time ever, I think, that people are able to create atomically precise nanostructures using cells, which is a very different, radical approach to technology. We are no longer designing the computer and building with a machine top-down how something moves. We design in the computer, but we take into account the evolutionary history of life on Earth, and then we go back to life to build our technology. And I think, as I will show you later, this is just one of the examples in which that shows how technology is changing. We are moving from top-down approaches to embracing biology complexity, not only to understand it, but to create new materials. And from those new materials, we're creating the new strategies of medicine of the future. So one example from these people, they created proteins that don't exist from nature, and then they created an artificial virus. And they put the artificial virus with an RNA in a culture with E. coli cells, and then the artificial virus was able to evolve. they hope this will be kind of the bacteria of the future. But again, it shows how a combination of computation, evolution, genetics, and physics is giving rise to a radical new way to manipulate matter and to create new medicine. DNA nanotechnologies are using a similar strategy to create ways so we can produce chemicals that are difficult to produce in normal organic chemistry. In biological systems, don't create chemicals in a bottle shaking it. They carefully sanitize the ribosome, put the things together. We are made of nanomachines that are able to put all the bits of a molecule in the right place. So these guys are trying to do the same. They're trying to build DNA structures together with proteins that they are able to synthesize chemicals that they are not able to be synthesized in the normal chemical industry. Another example from last week, actually, these guys find a new way of creating antibiotics to which bacteria cannot grow resistance to. So they created a structure that looks like a virus, but it's not a virus. It's made of pieces of protein. And these pieces of proteins are inspired by our own proteins when they fight disease. Then they assemble them in something like a viral structure, which is able to stick to bacteria and break them very quickly. So in their strategy, they're combining knowledge of proteins, knowledge of immune system, knowledge of physics to create a radical new way of making drugs that combines everything we know into a nanostructure designed by a computer. So what I'm trying to say here, if I manage, is that while we are having a lot of convergence in biology trying to solve medical problems, a key is this combination of techniques and going back to basics in the understanding of biology. So while drug designers or protein engineers have been trying to solve specific problems, physicists have been using this technique to put biology in a wider context. So, for example, one of the main questions we are making us these days is, what is the origin of intelligence? Why is the origin of life? And why is physics important in understanding life? So I just play you here this movie, if I can. Oh, I don't know how to play that. Anyway, I can't play these movies. No. Okay. So one of the things we're doing these days is trying to understand how and why biology emerged from the nanoscale, and how, for example, we're starting to think that molecules such as DNA or RNA emerged on Earth, and just by the interaction with the environment, they created a shape. When the shape persists over time, by dissipating energy into the environment and reducing entropy, that shape is embedding information about the environment. And that is why biological structures are able to become understanding of the environment and entangle with it. So what we are trying to do these days is trying to combine in the labs all these new maths, new experiments, new simulation to tackle increasingly complicated problems in biology, the interplay of molecules, how is the physics of evolution and the history of life on Earth. And we think this is important to embrace biological complexity. So as we saw in the previous talk, one of the main problems of medicine is that we can't continue in the reductionist approach to try to find new medical treatments. It's not only physicists, as you know, machine learning it also became good when it started to embed in its structures the structures of life. So before machine learning became good, the algorithms were also made top-down. But algorithms started to become better at recognizing the world around them when they mimic in the structure the connectivity of the neurons in the brain, for example. So all fields are slowly moving into understanding and linking physics, intelligence, chemical and complexity to understand biology. A beautiful example, for example, here is that not only algorithms become more clever when you interconnect the pieces of the algorithms in a layer structure, but even nanowires by themselves become able of computation. So this is a work by Jim Jimsevsky in UCLA, and they put a lot of silver nanowires on a plate, and by connecting them in many connections, a little bit mimicking again the connections of the brain, and then they were feeding the traffic, the statistics of the traffic of Los Angeles on one side of the chip. After a while, because you're so small at the nanoscale, the electrical signals start changing the mesh, and the mesh is able to computate the statistical pattern that you put in. So what we are learning is just matter at the nanoscale, just because it's matter at the nanoscale and it's highly interconnected, has the capacity of computation. And again, moving away from reductionism, we know that the biggest cancer treatments that are often offering hope for patients are not based on nanoparticles or chemicals, are based on immunotherapy. Again, we're moving away from the paradigm of drugs and genes and molecules and using the immune system, our own biology, to fight cancer. And in this context, nanotechnology is becoming important again. So instead of using nanotechnology together with pharmacology, people are using nanotechnology to train the immune system so it's able to recognize cancer cells. And they're doing it in many ways, using nanoparticles, or maybe perhaps the most striking is the development of materials, nanomaterials that are implantable. And inside of these materials, you have a lot of signals that the cells will recognize over time, and then you train your immune system to recognize cancer cells and get rid of them. So we are moving all our technologies away from sort of reductionism that we have for most of the 20th century. And we all together trying to interact with nature in a different way. So trying to deal with cells, trying to use cells to produce new materials, trying to use our own immune system to create better treatments for cancer. And finally, another thing I talk in my book is about using nanotechnology for regenerating tissues. So when you have a tissue and you have a wound, one of the reasons why you have a scar tissue is because the cells come and stick to the wound, and they find a material, and they don't have information, the nanoscale information that tells them how they have to behave. So by creating materials that reproduce the actual environment of the cells, you can heal without scars, for example. So people are using this type of thinking, creating nanoscale scaffolds to regenerate body parts. These days, the easiest things to do are the easiest tissues, so it will be skin, tracheas, and reconnecting neurons that have been injured, the connections in trauma. Perhaps the most interesting thing is not to regenerate tissues, but to create organs in chips that reproduce real organs that we have in our bodies. The reason why this is interesting is because people are learning to use these 3D printed organs and connect them with each other to create drug tests that don't need animals anymore. So instead of testing in animals or humans, you can do a lot of the testing of the drugs in little chips that reproduce organs at the micron scale. So what I predict is that in the future, we will have a kind of, in order to understand ourselves and to treat disease, we will need a kind of combination of real-time measurement of what is going on in the body. This will be a combination of nanotechnology, probably cells. We will be combining our sort of reductionist top-down approaches with emergent approaches. We will be having very mixed chips and ways of measuring the way we to get signals out of the body. This will require a smart mathematical model, artificial intelligence, and simulations to make sense. Artificial intelligence alone won't be enough because we will have too much data, and we will have terabytes of information about each of us, and just having a machine learning algorithm will not be enough. So we will need more physics, more smart mathematical modeling. And basically what we are doing is to getting closer to the dream of traditional medicine. So I don't know if any of you have got treatments of Chinese medicine, but in Chinese medicine, for example, they have these holistic approaches, and one example is the pulse takers. So in Asia, a lot of people they go to the doctor and they get a pulse. And in the pulse, they'll have someone that have been trained for 20, 30 years, machine learned for a long time, to understand a lot of signals, also looking at the patient's face, looking at how it feels, how it will react to make diagnostics. So it looks like we're getting there. We're going to start getting devices that are able to get our pulse, a lot of pulses, chemical pulses, physical pulses, and then get computers as well as the doctor to look at us with machine learning and indeed a smart mathematical model to diagnose our diseases. So I'm finishing. Another thing we're doing is to create things and to get inspiration to create things that don't exist in nature. I bring you a beautiful example. This is the cyber Stingray from Kevin Kidd Parker that he produces in 2016 that tells you a lot about the future to come. This is a little plastic toy made of a polymer. Inside the polymer, you have printed heart cells from mouse. And these heart cells respond to light. So by a careful combination of computer modeling, material engineering, and biology, he created a stingray that can follow the light. So we are witnessing convergence of science in biology. So nanotechnology, biology, physics, engineering, big data, algorithms are all converging in biology to transform the way they work, to get better robots, to get better algorithms, and to improve our health. And the main message I want to take you is that nanotechnology was key to take us there, and it still is key to take us there, not only because it gives us the machines and the tools to interact with matter at the nanometer scale, but because it led us to actually embrace biology's complexity. We cannot look at proteins or DNA isolated from the environment. They are bound for the environment, created very complex networks and very complex shapes that are linked with the environment, that are interacting continuously with the environment, and that our technologies are moving that way, and that physics will play a fundamental part in all this story. And I thank you for your attention.